Hello everyone and welcome back to the Calculus video lecture series. Today we are going to be covering a very important theorem in calculus known as the Fundamental Theorem of Calculus. So to get us started on what the Fundamental Theorem of Calculus is, we do need to talk about something called an area function. So let's say that you have a continuous function y equals f of t that is defined for all t values that are greater than or equal to some fixed number a. The area function a of x is going to give you the area of the region bounded between the graph of f, the lower limit t equals a, and some upper limit t equals x. And it is going to be defined as the area function a of x equals the integral from a to x of f of t dt. And what this function will do is it will give you the net area underneath the curve of y equals f of t for any interval of t between a and x. So just to kind of give you a sense of what these area functions do, we have here the graph of y equals f of t, and we have various regions that are given. So this region below the x-axis has an area of 27. This region here above the x-axis has an area of 3, and this region below the x-axis has an area of 35. Remember that any regions that are below the x-axis are going to have negative areas. And we have two different area functions. We have a of x equals the integral from -1 to x of f of t dt. And the area function capital F of x is going to equal the integral from 3 to x of f of t dt. So what these area functions are is they are definite integrals where the variable x is going to be plugged into your upper bound. So if we are evaluating the area function at 3 and finding a of 3, what we're doing is we are going to be plugging 3 into our upper bound in the area function a. So that will give us the integral from -1 to 3 of f of t dt. Now remember, area functions always give you net area. So this is asking for the net area between the graph of f of t and the t-axis from -1 to 3. So the area between -1 and 3 this region has an area of 27, but since it is below the x-axis, this area function has a value of -27. So then for the next one, to evaluate capital F of 3, what we're going to do is we are going to plug 3 into the upper bound of our area function capital F. So that will give us the integral from 3 to 3 of f of t dt. Might remember in the last video that when your bounds of integration are the same, there is no area, so the integral will come out to 0. I also apologize for the subtitles and how bad they are. If you want to, you can always go onto the closed captioning section of YouTube and you can turn on YouTube subtitles. Hopefully they will be better. All right, so now that you know basically what an area function is, there are going to be two parts to the Fundamental Theorem of Calculus. Part 1 involves area functions. So let's say that you have a continuous function f on a closed interval a to b. Then the area function a of x equals the integral from a to x of f of t dt. Remember, this is going to give you net area. Let's say that this area function is both continuous and differentiable. Then the derivative of the area function, which is going to be the derivative of that integral, will just give you f of x. So what this means is that the area function of f, which is that definite integral, is the antiderivative of f. So what that means is that this part of the fundamental theorem establishes that inverse relationship between derivatives and integrals. The differentiating operation and the integrating operation canceled each other out. So basically, when you take a derivative of an integral, derivatives and integrals are inverses of each other. So they are going to effectively cancel each other out, leaving you with just f of x. It's sort of like taking a square of a square root. Squaring and square rooting, when performed together, will cancel each other out. So if you take the derivative of an integral, those are going to cancel each other out, leaving you with the inner function evaluated at that upper bound x. This is why the general antiderivative is also called the indefinite integral. Integrals are antiderivatives. The second part of the fundamental theorem is going to establish the tie between definite integrals and indefinite integrals. So what we're going to do for this first part is we are going to find the general antiderivative of f of t equals t squared. So the general antiderivative is also known as the indefinite integral. So I'm going to take the indefinite integral of t squared, dt. So the integral of t squared will be t cubed over 3 plus c. Got a little carried away there with my plus c's. So for this next part, what we're going to do is we are going to evaluate this integral on a graphing calculator. We're going to evaluate the integral from 4 to 7 of x squared dx. Now, because it's hard for me to switch back and forth and keep the recording going, I am going to upload in a separate video how to evaluate a definite integral on a graphing calculator. So please just stay tuned for that video. It will be in the same playlist as this video lecture. So just go watch that video to learn how to evaluate this on a graphing calculator. But evaluated on a graphing calculator, you get 93. So what I want you guys to do is I want you guys to pause the video and take a few minutes to take the antiderivative t cubed over 3, the bounds 4 and 7, and I want you guys to see what combination of evaluating t cubed over 3 at 4 and 7 and doing any other arithmetic operation will give you 93. So pause the video now and take a few minutes to figure that out. So after a little bit of trial and error, you would have found that if you evaluate the antiderivative at 7, and then if you subtract the antiderivative evaluated at 4, you get 93. So that leads us into the second part of the fundamental theorem, which establishes the relationship between definite integrals and indefinite integrals. Both types of integrals are antiderivatives, and you are going to use antiderivatives to evaluate definite integrals by hand without a calculator. So capital F is going to be the antiderivative of the function lowercase f. So if you are evaluating the integral from a to b of lowercase f of x dx, that is going to be the antiderivative evaluated at b minus the antiderivative evaluated at a. So in plain English, what this means is that the definite integral is equal to the derivative of f of x evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So this part of the theorem establishes that both types of integrals are antiderivatives. So what we're going to do is we know that this should come out to 93. Let's actually evaluate this by hand. So what we're going to do first is we're going to find the general antiderivative, which is x cubed over 3 plus c. Then we're going to evaluate it from 4 to 7. Now, when you're evaluating definite integrals by hand, you always plug in the upper bound first. And remember, this vertical bar here means evaluated at. So we're going to plug in 7 first. We have 7 cubed over 3 plus c. Then subtract. If the antiderivative involves more than one term, you do need parentheses after the subtraction because both terms are being subtracted. Then we're going to plug in the lower bound, which is 4 cubed over 3 plus c. So then, when you do this, when you distribute that negative, you'll get 7 cubed over 3 plus c minus 4 cubed over 3 minus c. Some arbitrary constant minus the same arbitrary constant is going to cancel each other out, leaving you with just 93. In fact, when you are using antiderivatives to evaluate definite integrals, you are not going to need the plus c. Because what will happen is because these are always going to be subtracted, this process of canceling out the c's will happen every single time. I don't care what your function is. I don't care what your definite integral is. The plus c's will always cancel each other out because it's an arbitrary constant minus the same arbitrary constant. So when you are using general antiderivatives to evaluate definite integrals, you don't even need the plus c. You can just ignore it because they're going to cancel each other out anyway. However, anytime you are evaluating an indefinite integral which has no bounds, make sure that you do have your plus c. All right, so what we're going to do for this next one is we are going to evaluate this by hand. So the first thing that we are going to do is we're going to find the general antiderivative. So we're going to use power rule for all of these. So we will get, we are going to increase the power by 1 and then divide by the new power. Minus, leave the 6 alone. We're going to increase the power by 1 and divide by the new power. And then I'm just going to, tidy up my constants a little bit. My antiderivative is going to be 30x squared minus 2x cubed. And I'm not even going to bother with the plus c because this is a definite integral. The c's are going to cancel out anyway, so I'm just not even going to bother with them. Then I'm going to evaluate it from 0 to 10. So when you're evaluating a definite integral by hand, you're going to plug in the upper bound first. So I have 30 times 10 squared minus 2 times 10 cubed. Then you're going to subtract the antiderivative evaluated at the lower bound. Now, because the antiderivative involves more than one term, please, you must use parentheses here because both terms are going to be subtracted. So then we're going to plug 0 into our antiderivative, so we get 30 times 0 squared minus 2 times 0 cubed. And then when you do all of that arithmetic, you will get 1,000. So for this next one, we're going to take the function 3 sine of x dx, and we're going to evaluate the definite integral from 0 to 2 pi. So remember, the 3 is a constant multiple, so we're going to leave it alone. For the antiderivative of sine, you are asking yourself, what function gives me a derivative of positive sine, and that will be negative cosine. So we're going to take the antiderivative, negative 3 cosine x. We are going to evaluate it between 0 and 2 pi. So we're going to plug in the upper bound first. So we get negative 3 times the cosine of 2 pi minus the antiderivative evaluated at the lower bound, so negative 3 cosine of 0. Then when you evaluate all of that, you will get a net area of 0. Remember, definite integrals will always ever give you net area. So why did the net area come out to 0? Well, if you take a look at this function, 3 sine x looks something like this. From 0 to 2 pi is one complete period of this function, so that means the area above the x-axis here is exactly the same as the area below the x-axis here. Since areas below the x-axis count as negatives, that means the positive areas canceled out with the negative areas, giving you a net area of 0. So just keep in mind that integrals always give you net area. Now for this next one, there is no quotient rule for any type of integral. So when you see something like this, you're going to have to do a little bit of simplifying first to get this into a form that you can work with. So because the denominator just involves that one term, I am going to break up this subtraction in the numerator by writing it as a subtraction of two separate fractions, each with a common denominator. So I'm going to write this as, I'm going to first rewrite that square root of t as t to the 1/2 all over t minus 1 over t dt. And then at least for this first one, I'm going to use a little bit of exponent rules, and I'm going to subtract my exponent. So I've got the integral from 1/16 to 1/4 of 1/2 minus 1 is t to the power of negative 1/2. And remember, the only power that power rule does not work on is negative 1, because 1 over t is going to have its own antiderivative. So first I'm going to find the general antiderivative. So for this first term, I am going to use the power rule. So I'm going to increase the power by 1, which will give me 1/2. Then dividing by 1/2 is the same as multiplying by 2. Minus. Then for the integral of 1 over t, what function gives me a derivative of 1 over t? That is the natural log of t. Then I'm going to evaluate it between 1/16 and 1/4. So you plug in the upper bound first. So we're going to have 2 times 1/4 to the power of 1/2 minus the natural log of 1/4. Then minus parentheses around everything after this because both terms are being subtracted. Then we're going to plug in the lower bound, 1/16. So we have 2 times 1/16 to the power of 1/2 minus the natural log of 1/16. Then when you evaluate this, it's not exact. You're going to get approximately negative 0.89 somewhere in there. Now, for this next one actually tests the first part of the fundamental theorem, which establishes the inverse relationship between derivatives and integrals. So I'm going to tell you now that the derivative and the integral will cancel each other out. I'm going to take a few minutes to show you why. So I'm going to do this in the absolute longest way possible first to show you why the derivative and the integral cancel each other out. In the future, you do not have to do this the long way. You can just use the fact that they're going to cancel each other out. So I'm going to start by evaluating this integral, and then I will get to the derivative next. So evaluating this integral, I'm going to get the antiderivative, which is t cubed over 3, kind of ignoring the plus c. Then I'm going to evaluate it between 1 and 3. Sorry, 1 and x. There we go. I'm going to plug in my upper bound first, so I get x cubed over 3 minus 1 cubed over 3, which will give us an integral of x cubed over 3 minus 1/3. So that is what the integral came out to. The integral came out to x cubed over 3 minus 1/3. So then what I'm going to do is I'm going to take the derivative of that integral. So then taking the derivative of x cubed over 3 minus 1/3. What we will do is, we're going to move down the power, decrease the power by 1. Derivative of 1/3 is 0, and that gives you x squared. So you can see that the derivative and the integral canceled each other out, and what you were left with was this inside function here, evaluated at this upper bound right there. As long as the lower bound is a fixed number, the derivative of a constant is always 0. So as long as that lower limit is a constant, some sort of finite number like 1 or 0 or whatever, if the lower limit is a finite number, when the derivative and the integral cancel each other out, you were just left with this inside function evaluated at this upper bound, because the derivative of that constant will always come out to 0. So what we're going to do for these next two is we're going to use that shortcut. We're not going to do these the long way. In fact, at this point, you can't take the integral of sine squared by hand right now. So we're going to have to use the fundamental theorem for this. So the lower bound is a fixed number, 1, which means the derivative of that constant will come out to 0. And since we have a derivative and an integral performed at the same time, they are going to cancel each other out. So all we will have to do is take this inside function, sine squared t, and plug in our upper bound in for t. So those will cancel each other out, and that will leave you with the sine squared of x. Now for this next one, you really want the lower bound to be the fixed number and the upper bound to be your variable. So you might remember that if you need to switch the bounds of integration, you can, as long as you make it negative. So I'm just going to put a negative in front of this entire thing. And I'm going to switch my bounds, so I'll have 5 on the bottom and x on the top, and then square root of t squared plus 1 dt. So since my lower bound is now a fixed number, I don't know what I did. So since the lower bound is now a fixed number, that means the derivative of that constant is going to be 0. And when you have a derivative and an integral performed together, they are going to cancel each other out, leaving you with this inside function evaluated at the upper bound. So when those cancel each other out, remember we did still have that negative out front, That'll be negative square root of x squared plus 1. These problems should really involve no work because it is testing whether or not you know that derivatives and integrals will cancel each other out. Now for this next one, again, I'm going to do this in the absolute longest way possible to show you why it works out the way it does. And then after this, I do want you guys to do this a faster way and use the fact that derivatives and integrals will cancel each other out. Now, what's different about this is that the upper bound is not just an x, the upper bound is actually an x squared. The lower bound is still that fixed number 0, and we're taking the derivative with respect to x of the integral from 0 to x squared of t squared dt. So, just like before, I'm going to do this the long way. I'm going to evaluate the integral first. So, evaluating just the integral first, I'm going to get the general antiderivative, which is t cubed over 3. Then I'm going to evaluate it between 0 and x squared. So I'm going to plug in my upper bound x squared first, which will give me x squared to the third power over 3 minus 0 to the third power over 3, which I think we're all in agreement that comes out to 0, but, moving on. Then this is what the integral came out to, and just for this purpose, I am actually going to leave this as x squared to the power of 3 over 3 minus 0. You'll see why in a minute that I did not simplify those powers yet. So then we're going to then take the derivative of this integral. So taking the derivative with respect to x, of x squared to the third power over 3 minus 0. Now, because of the way I have it written, this will involve the chain rule. So the derivative of the outside, we're going to move down the power, leave the inside alone, and decrease the power by 1. Then we're going to multiply it by the derivative of the inside, 2x. When those cancel out, we are left with x squared times 2x. Now, I'm going to leave it like this because I want you guys to look for a shorter way to do this. If you'll notice, the upper bound just got plugged in for t in this function right here, which gave us that x squared. But then, because this is a derivative and this upper bound is a function of x, you would need to use the chain rule. So this 2x right here is simply the derivative of your upper bound. So when you have something like this where your upper bound is a function of x, you will plug it in for your t's in your function here in the middle, and then you're going to multiply it by the derivative of the upper bound because chain rule. So we're going to kind of use that shortcut to evaluate this derivative. So remember, if you have a derivative and an integral performed together at the same time, they are going to cancel each other out. So the upper bound is not just x, it is a function of x. So we're going to plug in this upper bound in for this t in our function, which will give us the cosine of x squared. Then we're going to we're going to multiply it by the derivative of the upper bound, which is 2x, and you can go ahead and leave it like this. So that wraps up the fundamental theorem of calculus. So the first part of the fundamental theorem gives you that derivatives and integrals will cancel each other out. The second part shows you how to use antiderivatives to evaluate definite integrals. So thank you all very much for watching, and remember, if you want better subtitles, you can always turn on YouTube's closed captioning feature and turn on their subtitles. Hopefully they're going to be a little bit better than this if you need subtitles. So thank you all very much for watching, and I will see you guys in the next video.